All right, today we're going to demystify object-oriented design. Now, this is a really fundamental idea that powers so much of the software that we use every single day. It's really a way of thinking that helps build applications that don't just work, but are also flexible and, easy to manage down the road. So, let's dive right in.
So, at its very heart, object-oriented design, or OOD as you'll hear it called, tries to answer this one huge question. How do you get a computer to think about the real world? How do we possibly model all these complex systems in a way that makes sense to us humans and to the machine? Well, the whole approach starts with a concept that we're all familiar with, literally from the moment we're born, the object. In software, an object really isn't all that different from a baby's toy. Think about it, right? A baby learns that a block has properties, like its color and its shape. That's its data. And it has behaviors. It can be stacked, it can be thrown. A software object is just that. It's a bundle of data that describes what it is and a set of behaviors that define what it can do.
So to be object-oriented, it just means we're designing our software by describing a whole collection of these little digital objects, and crucially, how they all talk to each other to get a job done.
Okay, but what if you're building a system with thousands or even millions of similar objects? Say, an inventory system for a huge fruit farm. You're not going to define every single orange from scratch, right? No way! You need a blueprint.
In OOP, that blueprint is called a class. Now, this is a key distinction. A class isn't the object itself, it's the idea of an orange. It defines that an orange has a weight and that it can be squeezed. The actual oranges sitting on your table, those are the individual objects, all created from that one single blueprint.
So how do we actually sketch out these blueprints and show how they're all connected? Well, designers use a standard visual language for this. It's called the Unified Modeling Language, or UML. And you can basically think of it as the architectural drawing for a piece of software. Having a shared language like this is absolutely essential, especially on big projects, because it lets everyone on the team understand the design at a glance. It really cuts down on miscommunication.
So this is what UML looks like at its most basic. You've got these two boxes representing our classes, orange and basket. And that line between them just shows that, yep, they're connected. They're associated in some way. It's a really simple but crucial starting point.
Okay, now we can add a little more detail. This is called multiplicity. See that star next to orange? That just means many. And the one next to basket means, you guessed it, one. So this diagram now clearly tells us that one basket can hold many oranges. See, it's getting much more precise.
Next, we add attributes. This is the data part of our object definition that we talked about earlier. So for an orange, that could be its weight, maybe the orchard it came from or the date it was picked. For a basket, it might be its location in the warehouse. And here it is, the final piece of our blueprint, the behaviors, which in the programming world we call methods. An orange object can be squeezed. A basket object can be sold. These methods are the actions, the verbs, that bring the whole system to life. Our blueprint is complete.
So we have our blueprints, but to build systems that are truly elegant and robust, designers rely on this really powerful toolkit of core principles.
First one up is abstraction. Just think about your TV remote. You press the volume up button, and the sound gets louder. You have no idea what's happening inside, the infrared signals, the circuitry, and you don't need to. Abstraction is the art of hiding all that messy complexity and just giving you a simple set of buttons to interact with.
This car diagram is a perfect example of that. A driver, well, they need a really simple interface. The steering wheel, pedals, that's about it. That's one level of abstraction. But a mechanic, they need a much, much deeper level, with access to the engine and the brakes. The same car, but with totally different interfaces for different users.
The next tool in our kit is composition, and this one is super easy to remember. It's the has-a relationship. It's how we build complex things out of simpler things. A car has an engine. A chess set has pieces. It's all about building stuff by assembling its component parts. Take a look at this chess diagram. See that solid diamond symbol? That's our visual cue for composition. A chess set is composed of, or has a, board and 32 piece objects, and the board itself, in turn, is composed of 64 position objects. It's just a really clear hierarchy of these part-of relationships. And finally, we've got inheritance. So, if composition was the has-a relationship, inheritance is the is-a relationship. This is when one class is just a more specific version of another one. A poodle is a dog. A rook is a chess piece.
And this diagram shows it perfectly. A pawn, a rook, and a queen, they all are specialized types of a more general piece class. They inherit the things all pieces have in common, like a color, but then each one has its own unique way of implementing the move method.
Okay, we've got our toolkit. Let's put it to work and see how we can tackle a real-world design problem, building a virtual library catalog.
All right, so here's a first attempt. And, at first glance it might seem okay, but look at all those connecting lines. It's a mess. Developers actually have a term for this kind of thing: spaghetti and meatballs. This design is super bulky, it's fragile, and it would be an absolute nightmare to try and add anything to it later on. But by applying our principles, we can totally restructure this into something way cleaner. Here, we've created a general library item class, and then used inheritance for the specific types, like book and DVD. We also generalized the ideas of authors and actors into a single contributor class. And the result? It's simpler, it's more flexible, it's just a far more elegant solution.
So, after all these diagrams and definitions, what's the big takeaway? Why does thinking in objects actually matter?
Well, here's the bottom line. Object-oriented design is way more than just a technique for writing code. It's a powerful mental model for taming complexity. It gives us a framework to break down any huge, messy problem into a system of smaller, understandable, interacting parts.
And that really all comes down to this idea. Whether you're building software, designing a business, or just trying to understand any complex system, the real power is in abstraction. It's knowing which details matter, and more importantly, which ones you can safely ignore. Thanks for joining me.